Hey Science Nines, it's Manchak here with your video lesson for Concept D3. So we've been working our way through our electricity units, and you should have completed already Concept D1, which introduced us to some ideas about electricity, including electrical safety, as well as some other considerations when it comes to things like static and current electricity. Then you moved on to concept D2, where we had a deep dive into looking at Ohm's law and different ways that we can describe electricity using things like voltage, amperage, resistance, those kinds of things. And we also had a quick look at electrical circuits, and hopefully you've done some work on the the circuits activity that I put forward for you, with the hope that you guys got some practice and a little bit better understanding of how circuits like parallel and series circuits work. What we are going to move into for concept D3 this week is going to be starting to look at some forms of energy, because we need to talk about this, because really electricity is all about energy, and flowing electrons are a form of energy, and talk about transformation of energy, and that means turning one form of energy into another form of energy. And then we're going to talk about electrical and mechanical energy and how we use transformations of electrical to mechanical or mechanical to electrical to our advantage. Now, this concept here is really dealing with a big idea in science, and that is that energy comes in many different forms, and we can't create or destroy energy. That's the law of conservation of energy, but we can transform it. We can turn it from one form to another. And a lot of our electrical devices do a really good job of taking electrical energy and turning it into mechanical energy, and we'll explain what mechanical energy is in a bit. Or we have electrical devices that take mechanical energy and turn it into electrical energy. So we're really going to have an exploration of that in this unit. So we're going to talk about things like forms of energy, transformation of energy. In particular, we're going to look at motors and generators and how they work. We'll talk about AC versus DC current, so the movement of electrons and how it's different in those. And then there is more than meets the eye to this concept, and we'll talk a little bit about transformers as well. Your textbook pages you'll cover in this unit are, or in this concept, pardon me, are 319 to 331. I've got a whole whack of different videos on here. Most of them are just accessories to the stuff I'm going to be talking about to give you a little bit more background. You don't have to watch all of them. If I was going to pick a few of them, I would look at how an electric motor works for sure and try to have an understanding of that. It might be worthwhile having a look at this AC versus DC kind of stuff, and then maybe how does a transformer work. But that's really up to you. These are just accessories beyond what we have for this particular concept. Then we're going to move into some formative work, just some questions out of your textbook. There's a worksheet, and then a practice quiz, and of course a summative quiz as always. So I think without any further ado, I am going to shift this image over to here, and we're going to hit present and get started on this concept with you guys. So this is concept D3. These are the outcomes that we're going to be covering. So we're going to identify, describe, and interpret examples of mechanical, chemical, thermal, electrical, and light energy. We'll investigate and describe the evidence of energy transfer and transformation. We'll construct and use devices for transforming mechanical energy to electrical energy and for transforming electrical to mechanical. Normally I would do that in the classroom and we'd play around with a motor and a generator, but because we're doing this remotely now, you may want to look around your house for some of those items or watch a couple of the videos, and that'll give you an idea, since we really can't construct and use them together, right? And then we'll look at, again, evaluating how these devices work and how we can evaluate those devices. So first thing we're going to do in this section is energy forms and transformations. So there's lots of different kinds of energy that exists out there in the world, and it's all governed by the law of conservation of energy that says energy can neither be created nor destroyed. It can only change forms. What is energy? Well, energy is the ability to do work. And work, if you recall from Science 8, is when we exert a force on an object and move that force over a certain distance. And the force and the direction of the movement have to be in the same direction. So we're doing work on an object, so we're moving an object over a certain distance, and energy is the ability to do work. More energy something has, the more ability to do work. The less energy something has, the less ability to do work. So, when you're sitting in front of your computer listening to me drone on and on and on about science, and you're starting to nod off, well, your energy levels are dropping a little bit lower, and that means that your ability to do work is not so good. Okay. In this case, we're talking about certain kinds of energy that I wanted to highlight with you. So the first kind of energy, and I want you to know these 4 kinds of energy because we'll use them again next year in Science 10 and in years beyond. So learn them now, less work to worry about later next year. So chemical energy is the energy that's stored in chemicals. Remember, in chemicals are composed of atoms, and those atoms are held together by bonds. And there's a couple of types of bonds that you probably talked about in Unit B, which are covalent bonds where we share electrons, and there are ionic bonds where electrons are stolen from one entity and taken by another, and then they're held together by electrostatic charge. Well, in a chemical, energy is stored in these bonds. And when the energy is stored inside a chemical, so imagine some sugar, right? It's a chemical and it's got energy stored inside it. It's being stored as potential energy. That energy is there, but it's not being released or used at that point. When it's released, when the bonds of glucose or of the sugar are broken in a chemical reaction, it releases that energy, and that energy then can do work. When we release that energy, that chemical energy changes over to another kind of energy, usually kinetic energy, which is the energy of motion. Okay, so that's one example. So chemical energy is the energy stored in chemicals. Electrical energy is the energy of charged particles. I like to think of it simply as the energy of electrons flowing or moving in some way. So remember, electrons are negatively charged, and electrical energy is transferred when these charged particles travel from place to place. So electrical energy is electrons moving. Okay. Usually we employ electrical energy in wires as we move them along a conductor like a wire. As those electrons move, they have the ability to do work for us, so they are considered to be energy. The next kind is mechanical energy, and this is the energy possessed by an object because of its motion or its potential to move. So I like to think of mechanical energy as a machine doing work, right? And the more mechanical energy a machine has, the more ability it has to do work for us, to lift heavy objects, to move things from one place to another, okay? And then the last type of energy, and sorry, I should jump back. Mechanical energy is really strongly linked to kinetic energy. Kinetic energy is the energy of motion. A heavy object moving very fast has a lot of kinetic energy. A small object moving very slowly has very little kinetic energy. And machines take advantage of generating kinetic energy to do the work that they do. The last type of energy we're going to deal with is thermal energy. And thermal energy is the total kinetic energy of a substance. This one's a little trickier to try to understand because all matter is made up of particles. And these particles we know are always in constant random motion. And you guys learned about this in the first unit of Science 8, that particles are always moving. The warmer or the hotter a particle is, the faster it's moving. The slower a particle or less energy the particle has, the slower it's moving. If we take, let's say, a cup of water, and we add up all of the kinetic energy inside that cup of water, that gives us its thermal energy. The faster the particles are moving, or the more energy they have, then the higher the kinetic energy of that substance and the higher the thermal energy in total it contains. So I kind of like to think of thermal energy as heat energy. The hotter something is, the more thermal energy it has because the particles are moving faster, they have greater kinetic energy, and the lower the temperature of something, the lower the thermal energy, the lower the kinetic energy, they're not moving as quickly. Okay, I hope that makes sense to you. So please take the time to learn chemical, electrical, mechanical, and thermal energy. So I wanted to talk a bit about chemical energy because it's super important for us. It's the energy that's found in chemicals, including food. So we already talked about this. Glucose molecules, which are sugar molecules, are used in our body cells to produce thermal energy and mechanical energy. So when we take a glucose molecule and we break it down through the process of cellular respiration, that energy in the glucose molecule is gradually released, and what happens is we release a little bit of heat energy, thermal energy, and some kinetic energy or mechanical energy that allows us to do work with it. Okay, the chemical energy can also be converted into mechanical energy or sound energy. For example, if you take a battery is a chemical reaction, so it contains chemical energy. And when we plug a battery into a CD player or into a flashlight, what we're doing is we're taking chemical energy and we're converting it into light energy. If we put it into a CD player, it's converted into sound energy. Okay, so we're seeing energy transformation taking place here. Chemical energy can also be transformed into mechanical energy with heat and light as the products of it, right? For example, if you had a stick of dynamite, there's a whole bunch of chemical inside that stick of dynamite. When we light the fuse, and that fuse provides just enough energy to kick off the chemical reaction, kaboom, it explodes in a whole lot of heat and a whole lot of light. Okay, so that's what chemical energy is. Chemical energy is stored energy until we transform it to something else. So some transformations involving chemical and electrical energy. These are just some examples. So let's say we have a toaster, which is our device. The input energy, okay, is electrical energy. We plug our toaster into the wall, we turn it on. Then the toaster takes that electrical energy and transforms it into thermal energy, which is the little coils that you see inside your toaster heating up the toast to brown it for you. Okay, excuse me. The another energy conversion we talked about happens in a flashlight. The batteries have chemical energy inside them, and when we flip the switch for the flashlight and turn it on, it's converted initially to electrical energy as a little circuit is run, and then that electrical energy flows into the bulb and allows the bulb to turn on and create light. And maybe some thermal energy, because there's always a little bit of waste created by this. Electrical energy can start out with a blender, right? A blender, plug it in, turn it on. We have electrical energy flowing through the circuit in the blender, which eventually turns the little wheel on the blender that spins the blade, which is mechanical energy. Okay, so that's all I'm going to talk about for those transformations. So all of the devices, or many of the devices that we have around our houses, you can pick one up and you can determine what is its input energy and what is its output energy. How do we get from usually electricity in the form of chemical or electrical sources into some sort of output energy? So I'm going to take a sip of water because I need one. All right, so transformations between thermal and electrical energy. And this is a really interesting one. And we have these in our houses, but we don't always notice that they're there. And we can transform thermal energy to electrical energy and vice versa using something called a thermocouple. Okay, and a thermocouple is a device that can convert thermal energy into electrical energy. And this is be the point in class, and I don't have it with me because I didn't remember to bring everything with me, where I'd bring out an old thermostat from a house that I had up in Slave Lake. And we would have a look at a little coil of metal inside there that helps to make this whole thermocouple work. So a thermocouple consists of two different metals, a bimetal, bi meaning two, joined together that conduct heat at slightly different rates. And what happens is, because they conduct heat at slightly different rates, when heated, the difference in conduction results in a little tiny bit of charge or electricity flowing from one metal to the other. When we hook up that thermocouple to a little bit of a circuit, what we can do is that when the object is being heated, that circuit will sense that little tiny bit of electricity flowing, and then we can make it do something, flick a switch, for example. So thermocouples are useful for measuring temperatures in areas that are difficult to access or too hot for a regular liquid-filled thermometer. So one place where you might find a thermocouple is in your furnace to register how much heat is moving through your furnace so that it knows when to shut off so it doesn't overheat. So ovens also have this. Heaters, space heaters, those kinds of things will have them as well. But they instead are going to convert electrical energy into thermal energy because they're going to take a direction that you need to be at this temperature, and it's going to send a little bit of a signal to register that we need to go hotter or colder. Depending on the situation. So I believe I have a diagram here of what a thermocouple might look like. So this is a very simple thing, is we could take a piece of iron wire and a piece of copper wire, wrap them around each other. And then what would happen is apply a heat source to it. That heat source would mean that one of these two would heat up faster than the other, and that would create a little flow of electrons along the wires. And then when that flow of electrons hit a voltmeter, it would register a voltage, okay, which would mean that we've got moving electrons taking place in this thermocouple. If you're interested in learning more about these, there's tons of great videos on YouTube to have a look at for thermocouples and understanding energy transformations. Okay, so the big bit from this first section here is understand the kinds of energy, and then understand that energy can't be created or destroyed, so we can only make it change forms from one form of energy to another. And a lot of our devices that we use are powered by energy transformations. My calculator is being powered by the batteries that sit in the back of the calculator, right? And those batteries are transforming chemical energy into electrical energy that makes the screen light up and allow me to do my calculations, and it runs all the circuits that are inside the calculator. Okay, so what I want to move into now then is talking about how we take advantage of specific energy transformations, including the ones that include electrical and mechanical energy. So these energy transformations involving electrical and mechanical energy are extremely valuable for us. And when you take the time to think about what might have a motor, an electric motor in it, or where would a generator be involved in our lives, you may find a number of places where it pops up and you're going to go, holy smokes, I never thought about that before. So I wanted to talk about one thing. Deflection of a compass needle using an electric current showed that there is a relationship between electricity and magnetism. And so what I'm talking about now is a little bit of history. Is we discovered that there is something that happens when there's electricity moving through a conductor and when it's put nearby something that is magnetic. And the simple bit is that if you could try this at home too, is if you could find something where there's a lot of electricity flowing through it, you could put a magnet, a compass, very nearby it, and you would see that the compass needle would move. And because as the electricity flows along a conductor, it generates a magnetic field, just like a magnet generates a magnetic field. Okay? Remember way back at the beginning of the unit, we talked about the fact that opposites attract and like things repel. And we talked about charges doing that. Well, not only do charges do that, but magnetic fields do that. Right? The north pole of a magnet will attract the south pole of a magnet, and those two magnets will come together. But if you take the north pole of a magnet and put it nearby the north pole of a magnet, they will repel. You can't bring them together properly. Okay? So those same principles of attraction and repulsion in electric charge apply to magnetic fields. So just a couple of names. Oersted found that current created a magnetic field around a wire. So when current runs through a wire, electrical current runs through a wire, it generates a bit of a magnetic field. More current, more magnetic field, less current, less magnetic field. But a magnetic field nonetheless. Okay? And then what Faraday did after that is he was able to construct the first motor, electric motor, based on the fact that energy moves or current flowing through the wire can interact with a magnet and cause motion. We can cause mechanical energy to happen. There's a video that you may want to watch right at the end of the list of videos called World's First Electric Generator, and he goes just into a really quick discussion about how the first electric generator was created. So all of this leads to talking about electric motors, and electric motors operate off of some very simple principles that we've been working with for hundreds of years, or at least a couple hundred years. And the first principle is that what we just talked about, when electric current flows down a conductor, it generates a magnetic field. Okay, so what we need to do to create an electric motor is the first thing we need to do is create an electromagnet. An electromagnet is something that has a bundle of wire, usually copper wire, coiled around an iron core, and when we run electricity through that copper wire, it generates a magnetic field. Okay, so when attached to an electrical field, this electromagnet, or to electrical source, pardon me, this electric field, or bleh, let's try that again. When this electromagnet is hooked up to an electrical source, it produces a strong magnetic field. To keep the electromagnet spinning in a magnetic field, the direction that the current is traveling through the coil is switched. This creates what we call an alternating current motor. And it's accomplished by having a gap in a part of the electric motor, which allows the polarity to change. So I'm going to show you a diagram in just a second, but the first thing I want to introduce to you are the parts of an electric motor. So an electric motor has an electromagnet. We just talked about that, which is a bunch of copper wire wrapped around an iron metal core, and when we run electricity through it, it generates a magnetic field. Okay. The other parts of an electric motor that we need are a commutator. Okay. A commutator usually is a ring that has a split in it that breaks the flow of electricity for a moment, then reverses the flow in the coil which reverses the flow when the contact is broken, and so we break the magnetic field briefly. Okay, and I'll explain how that works in a second. We also have brushes, which are contact points with the commutator. I'll show a diagram and we'll try to make this make sense, which allows us to reverse the flow of electricity through the magnetic field. And then we have an armature. And the armature is the rotating shaft on which the coil, with the coil wrapped around it, spins. And where that coil is usually sits inside a big magnet. And when it starts to spin, it keeps spinning. And then we can hook the other end of that armature up to something. To a pulley, to a set of gears, something like that, that will allow us to take advantage of the motion that's being created. We are turning the electricity that's flowing through the coil, right, the electromagnet, we're taking that electricity and we're converting it to mechanical energy that causes the armature to spin. So this here is a very, very simple electric motor. Okay, we have, and I'm going to break this down a little bit. Okay, this right here with the arrows on it, okay, this is our coil. Okay, this is our electromagnet. That electromagnet, if you follow the circuit here, okay, is hooked up to, what's this? This is a battery, okay, a power source of some sort. And so electricity is going to flow out of the power source. It's going to hit this brush, okay, which is just a contact between this thing called a commutator and the brush, okay? And what it does is when the commutator is oriented like this, the circuit is complete and electrons flow through the coil and over back this direction, okay? You'll notice here that there's a split on the top and on the bottom. What happens is as the armature spins, and there would be a stick coming out of this that might be hooked up to a pulley or a gear, and when the armature spins, what happens is this whole commutator spins as well. And there will become a point when the brushes are not in contact with the metal on the commutator. At that point, the electric circuit is broken. Okay, and then it continues its rotation, excuse me, and has contact and the flow begins again. So as electrons are flowing through this coil here, and this is a very simplified coil, what happens is this flow of electrons is generating a magnetic field. And that magnetic field is interacting with this magnetic field here that's being created between the north and south poles of these magnets. And so that interaction between the magnetic field being generated by the magnets and the magnetic field being generated by the electromagnet, the coil with electricity running through it, means that we have two magnetic fields that can interact. And when those two magnetic fields interact, we've got attractions and repulsions that cause that commutator here to spin. Okay, and you'll see that it rotates clockwise in this case. So it's going to spin in that direction. And if we had something hooked up to the armature here, then the armature is the spinning part, then we would have the ability to make something happen. So at this point, it would be a good time to hit pause and watch this 1:30 video on how an electric motor works. See if you can wrap your head around what's going on. What I want you to get and walk away from all of this, okay, is that an electric motor takes electrical energy that comes from our power source as it flows through the coil, and it generates a magnetic field which interacts with another magnetic field. And what it does is it takes that electrical energy and turns it into mechanical energy. Mechanical energy can do work for us. Okay, does that make sense? Okay, so pause if you need to, and I'm going to move on. One way we can look at this is sort of thinking about a steering analogy, and this is really just describing what's going on with the commutator, and sort of imagining that a steering wheel is similar to turning an armature in a motor. At some point, we have to let go of the wheel to start again, and this is what the commutator allows the armature to do, is it takes a break for a second and allows us to come and continue with that energy. Okay, don't get too hung up on that. It's not necessarily the most important thing for you to know about this. Electrical energy to mechanical energy is an electric motor. That's important. You need to know that. Okay. At this point, I wanted to just take a second to talk about direct and alternating currents. Okay. Some motors run on direct current. It is direct because electricity will flow only in one direction. Okay. And if, that means that electricity is only going to be flowing in this direction, and it never flows in any other direction. Okay, if you want to see how a DC motor looks, then go into the Google Classroom and watch this short video on that. An alternating current means that energy flows back and forth within that particular motor at about 60 times or 60 cycles per second, at least here in North America, 60 cycles per second. What I would invite you guys to do is watch these videos and then maybe just have a quick look at what AC and DC current mean, and then move on from there. Really, to me, can you define them? Understanding the physics behind it is a little bit more than I want you to know at this point. So, what we're moving on to next then, and this is the last little bit for this concept, is talking about transformers. Okay, and I told you in this concept that there is more than meets the eye, and so here it is. And I'm going to take a sip while I let that sink in. So, where we're at with transformers is what they allow us to do is change the amount of voltage with hardly any energy loss to something. Why I care to talk about transformers is because they tie motors into generators and allow us to see how movement, that came out weird, how movement or motion or mechanical energy can be used to generate electricity, and how we can take maybe even just small bits of electricity and amplify the voltage so that we can transmit it over a large distance. Okay, so transformers are used to change the amount of voltage with hardly any energy loss. Voltage change is necessary because the most efficient way to transmit current over long distances is at high voltage and then reduce it down when it gets to its destination. So, imagine this scenario. You've got a generator somewhere. Let's say that generator is actually hooked up to a big hydroelectric dam. And so you've got water flowing over these turbines. These turbines are spinning as the water goes over, right? And those turbines are spinning. Those are attached to an armature, which has a coil sitting inside a big magnet. Well, I've just described a generator. As this spins, the coil spins inside the magnet, and as it spins, we're generating electricity in that coil. Okay? The problem is that every time as we move electricity down a wire, a little bit of energy is lost. But what we found is if we can take low voltage electricity and turn it to high voltage electricity, it minimizes energy loss. So that means that at my hydroelectric plant, where my generators are generating electricity, if I had a transformer that allowed me to step up my voltage from low voltage to very high voltage, I could then transmit my electricity that I'm generating down a wire to somebody's community. Okay, then we send it off to Riley. And then in Riley, what we do is we take that high voltage electricity and we step it down into lower voltage electricity to send out to the homes in our neighborhood. Okay, so the whole purpose, or one of the big purposes behind a transformer, at least for transmitting electricity from point A to point B, or where it's generated to where it's used, is because transformers allow us to shift the electricity up to super high voltages, which means we minimize energy loss as we get the electricity there, and then we can step it down again, and so that we can use it in our homes. Okay, high energy transmission lines are putting tens of thousands of volts of electricity through them. We're using 120 volts in our houses, so we need to step up to transmit and step down when we get back to the place where we're going to use. If you want, have a look at this video on how a transformer works. It's in the Google Classroom and it sort of helps you out. It has nothing to do with Optimus Prime, I'm sorry. This is just a simple diagram of what a transformer looks like. You could have a look at page 329 of your textbook as well, just for a quick look on that. Transformers are used with alternating current, and some transmission lines can carry up to 500,000 volts depending on the size of them. You don't want that running into your house, because not only is it ridiculously dangerous, but it will blow every single fuse in every single system in your house. So a step-up transformer increases the voltage, and how it does this is you can sort of, you put wraps around the coil. The more wraps on the coil, the more you're going to increase or reduce the voltage. So if I had, let's say, 5 wraps over here, and I had 60 wraps around of the wire around the coil over here, then this would be a step-up transformer. So less coils, more coils, steps up the voltage. If I had more coils here and less coils here, it steps down the voltage. Okay? So all of this leads us into talking about generating electricity. And generation of electricity is done through something called electromagnetic induction. Remember when I was talking about the hydroelectric dam, and we got water rushing over the turbines, and that turbine is spinning, and at the other end of that turbine, attached to an armature, is a coil of wire, right, sitting inside a magnetic field. That is electromagnetic induction. So the generation of electric current in a conductor by a changing magnetic field. As that coil spins inside that magnetic field, it's generating a flow of electrons. And this was accomplished and discovered by Michael Faraday almost 200 years ago. And he demonstrated that electrical current could be generated by moving a conducting wire in a magnetic field. That's his device right here. Is he could generate a flow of electrons hooked up to wires here as he spun this wheel inside the magnetic field generated by these magnets. By moving it back and forth through the field, Faraday created the first electricity producing generator. Okay, and so a generator then is the opposite of a motor. A motor uses electrical energy to make mechanical energy. Or to transform to mechanical energy. A generator takes mechanical energy and transforms it into electrical energy. Okay, what we do now is much more complex than that. We take massive coils of wire rotating in huge magnetic fields, which can produce enough energy, electrical power, to power an entire city or town. Okay, so massive, massive scenarios going on. So you could have a look at this video. I've already mentioned it earlier on, but you could do it as well. This is another diagram of what Faraday's disc dynamo looked like and how he used a magnet, and we had brushes, and he had a copper disc that was spinning, and there was a flow of electrons that was created out of this, and he could register it on a voltmeter, which I think is really kind of cool. Our operations are way, way, way bigger than that. Okay, there's two kinds of generators. There's a DC generator and an AC generator, and I don't want you to get too hung up on them other than just know the difference between them. A DC generator is much the same as a DC motor. The spinning armature produces electricity, and if the electricity is passed through a DC generator, it will spin like a motor. Okay, so we basically, it's that armature spinning inside the magnetic field. Now, an AC generator has a loop of wire attached to two slip rings, and the current is switched as the loops move up and down alternately through the magnetic field. The slip rings conduct an alternating current through the brushes, and then the brushes are hooked up to our electrical circuit, which transmits the electricity. This is just a diagram of what a DC versus an AC motor might look like, and just notice how the brush arrangements are a little bit different on here. One of these is going to be alternating in between being in the magnetic field and not being in the magnetic field. Okay, and so that means that current might be going in this direction or in this direction, depending on which of these is in the magnetic field at that point. That's what generates the alternating current. The direct current means that these are always almost always in contact as the armature is spinning. Okay, so the big bits on here, I don't really want you guys to get too deep into trying to understand exactly what an alternating or a direct current generator looks like. I don't want you to really get, I want you to understand the basic parts of a generator or a motor, and luckily they're the same thing, right? You've got an armature, which is the part that actually does the spinning, and attached to that armature is a commutator, brushes, and a coil, and it's all spun inside of a magnetic field generated by a big magnet. I want you to know the bits and pieces, but I really want you guys to understand that motors and generators are all about energy transformations, transforming one form of energy to another. If you're in a motor, you're taking electrical energy from a power source, whether you plugged it into the wall or whether you got hooked up to a battery, and you're taking that electrical energy and you're transforming it into mechanical energy that then a machine can use to do it, to accomplish its purpose. In a generator, we're reverse engineering that. What we're doing is we're taking mechanical energy, the spinning or the spinning of a turbine usually is what happens, and then what ends up happening is it spins that armature of that generator. That armature with a big coil attached to it spins inside that magnetic field. And through all of this, it's the interactions between electricity and magnetic fields and flowing electricity, which generates its own magnetic field, how those interact with the two of them to generate electricity or to generate motion. Okay, if you want to look more into this, all of our electricity generation that we have in Alberta is operating off of these basic principles, save for solar energy generation. That works off of something a little bit different, but our hydroelectric dams, our turbines, the water flowing over turbines spins the turbines and causes the armature to spin inside the magnetic field, generates electrons. Coal-fired power plants, what they do is they burn coal. That coal is used to heat up water. That water creates steam. That steam is pumped at high pressure over a turbine, causes that turbine to spin. That generates electricity, right? So think about it that way. Same thing would be true for a nuclear power generator. We're using a very controlled nuclear reaction to boil water, turn it into steam. That steam helps to spin a turbine. That turbine spins inside, or an armature spins inside a magnetic field and generates a flow of electrons. Solar energy is a little bit different, and that's for another lesson another day. So that is the end of this lesson. So what you can do right now is to jump on into your textbook and just have a look at the questions on page 331. And then we have worksheet number 3 that you can have a look at. Once you've done those two things and you're feeling confident, jump on to the practice quiz on the Google Classroom. Do the practice quiz and then wait for my feedback before you consider doing the summative quiz. So that's it for Concept D3. I will see you guys again for Concept D4. Stay healthy and we'll talk soon.